One of the most notable properties of the transition metals is that they form colored complexes. So this is notes F of chapter 3. Before we talk about how transition metals produce unique colors and why, first I want to review quickly what makes a color be emitted from an atom in the first place. So an electron likes to hang out on the ground state. That's Aufbau's principle. Electrons are lazy. Go to the lowest energy level. If that electron were to absorb energy, it could be promoted to an excited state, an available open orbital that is further from the nucleus. However, that electron's not going to stay there. Because of Aufbau's principle, it will automatically return to the ground state. In order to do that, it's going to have to lose energy. And that energy that's lost would be emitted in the form of a photon. The amount of energy that photon has will dictate what color we see during that emission process. What's really interesting is that the amount of energy really depends on the distance between the ground state and the excited state. There's going to be a specific quantum of energy released depending on where exactly these orbitals are located. So these distances actually determine the energy and therefore the color. So when we look at what's unique about transition metals, we're going to see a difference in the distance orbitals are away from each other. Keep in mind as we go through this that the energy of an electron is pretty much equal to the distance from the nucleus. For an electron, those are two things that are pretty much meaning the same thing for them. So there's a new term here, degenerate orbitals, would actually refer to equal energy orbitals, which is what we have always thought we had. 5D orbitals should have the same amount of energy. When you describe 3D compared to 4D, you would expect 4D to have more energy than 3D because 4D is further away from the nucleus than 3D. However, all 5 of the 3D orbitals have always been treated as if they had the exact same amount of energy. And for most atoms, they do. But for transition metals, we can actually split so that we would have different energies. Some d orbitals would have more energy than others. This is then going to create different types of transitions and can even just emit color moving between the d orbitals if we're bouncing from ground state to excited state and back within the d orbital now. So for this lesson, I want to focus on the transitions just within the d orbitals so I can look at the colored complexes that would be formed from our 10 transition metals. In the example to the left, the 3d orbitals on the bottom would represent a possible ground state, and then the 2 higher d orbitals would represent the potential excited state. So one possible transition that could produce color would go from maybe a d orbital in the ground state up to the excited state and back, and that energy emitted then as a photon would have to correspond with a specific wavelength of light. And again, that distance between the excited state and the ground state will dictate exactly how much energy is used. So in order to determine then the frequency of light, you can use the formula delta E equals Planck's constant times the frequency. So basically you take the energy and divide it by Planck's constant, and you can then find what color light, what frequency of light we have on our electromagnetic spectrum. Before we move on, I want to take a second to point out this new notation that they're using to identify the different orbitals. We talked about the magnetic quantum number a bit when we looked at the p orbital. It's a little easier to explain with the p orbital. P sub x would represent the p orbital that is oriented on the x-axis, whereas that orientation would flip to be along the y-axis for p sub y, and it would be coming towards you and away from you on the z-axis for p sub z. Those are the 3 possible orientations for your 3p orbitals. The d orbitals get a bit more complicated, and there are some specific subscripts that will try to describe these shaded regions inside the d orbitals. So you see here dxy, dxz, dyz, dz squared, and dx squared minus y squared. Kind of a crazy one. You do not need to know which orientation each of these represent, but you should be comfortable enough to see them and know that they represent the 5 different d orbitals. So as we look at the next example, you can see the 5 different d orbitals just written with their magnetic quantum numbers, the xy, the xd, and so on. Here we have 1 electron in a lower energy level, so this would represent the electron being in its ground state. Now, if it is exposed to lighter energy of some kind, it would absorb energy, which means that electron in the ground state would then be promoted into the ground state. So after light absorption, we can see our electron is in an excited state, or one of the higher level d orbitals. And that orbital would have more energy. The energy was absorbed. This brings up an important point. There has to be light or energy absorption in order to promote that d electron. If there was no light, if it was completely pitch black or no other energy being put in, you wouldn't ever get emission because there would be no promotion into the excited state to start with. When a compound absorbs white light, it is actually absorbing all of the different colors based on red, green, and blue primary colors and all the combinations in between. The color that we see is then dependent on which colors are missing. For example, with a copper ion, it looks blue, and that is because the copper ion is very good at absorbing yellow light. If yellow light is missing from white light, you would see the complementary color of yellow, which you can see in the color wheel here, is blue. So we see blue because yellow is absorbed. Now that was a very simplified color wheel, so here's a little bit more of a detailed one, where you can see that blue is actually opposite more of an orange color, yellow is opposite more of a violet color, and red is opposite green. Those 3 pairs are sometimes really important. I've had to actually memorize them for some chemistry classes before. And I have a really silly memory trick that might help you. Alright, it's called the Royal Christmas Dolphins. Sounds silly, but here's where that comes from. Violet and yellow are the colors of royalty. Red and green are the colors of Christmas. And blue and orange, good old football team, the Dolphins. So Royal Christmas Dolphins are main color combinations for the most important complementary colors. This was the main idea behind your Spec 20 lab. Whatever the beam color was most absorbed when it was the complementary color of the solution's color. Since the color absorbed depends on the distance or energy levels of the d orbitals, the last thing we have to go over is what is it that could cause that separation to be different in order to create a much higher energy level for the excited state to have that separation instead of having 5 degenerate, have them split. How big is the split between these energy levels? So there are 4 main factors that determine the separation between the d orbitals. So the first factor is the nuclear charge, or the pull from the protons in the nucleus. This also speaks to the fact that the identity of the metal plays an important role. For example, we know that zinc does not have any empty energy levels or any places in the d orbital where an electron could be promoted to. It has 10 electrons completely filling the d orbital. It can't promote an electron up to a higher energy level, so it's not going to have an opportunity to absorb any colors or any wavelengths of light, and so we don't see it creating any kind of color here. Here's some examples of pretty colors formed by some other transition metal solutions, and zinc is sitting here with no color. This is going to sound really silly, but if you're taking the IB test, pay careful attention. Colorless and clear are 2 completely different things in IB's eyes. I realize that that's a little silly, but they will not give you any credit for the word clear if the word they were looking for is supposed to be colorless. It is lacking color because it has not absorbed any other wavelengths, so the white light is intact. Colorless is different than clear. I think they see the word clear as meaning more like transparent or slightly see-through, not just actually lacking color, which colorless definitely means absolutely lacking color. The next factor depends on the ligand. Remember, the ligand is the substance with lone pairs or non-bonded pairs that's attached to the transition metal. So for example, water or ammonia. We're going to look at different types of ligands here in a minute, and you'll see that the more electron density you have, the more repulsion you're going to get, and so you're going to have different types of splitting based on what that ligand density is, how many electrons are in one spot on that ligand. So let's talk about charge density for a minute, just comparing water to ammonia, two compounds you should be fairly familiar with. Water is a bent structure with two sets of non-bonded electrons, or two lone pairs, where ammonia only has one. So one big idea is that non-bonded electrons have the most repulsion. So the most repulsion between any electron pairs would be felt between the non-bonded pairs on the water. Second to that would be the repulsion between a non-bonded pair and a bonded pair. And then last but not least would be between two bonded pairs, like between two of the hydrogens on either atom. So we get the most repulsion over here on the water. When we have a lot of repulsion, that means these electrons are going to spread out. So when you have a higher charge density, that would mean that they are closer together. The higher charge density is happening in the ammonia because you have more bonded to bonded repulsion, which is weaker than the non-bonded repulsion happening in the water. So when you have this increased charge density in the ammonia, you're going to see a greater splitting in the d orbital. So you see that the ground state and excited state of these d energy levels are way further split than between the two sets of d orbitals in the water. That water has less charge density, and so the d orbitals are not split as greatly. Across the bottom of the screen here, you see the low charge density ligands on the left, something like iodide ion, which would be completely full of lone pairs, all the way up to your cyanide ion, which has a triple covalent bond and a very high charge density. The higher the charge density, the stronger the splitting will be. You'll get a larger split in something like cyanide. And you see in the middle here the water versus the ammonia, like we just discussed. The ammonia had a higher charge density, and it's going to be higher up on this list. Let's take this one last step and tie the splitting in the d orbital to the color. Now, the higher the charge density that we have, the stronger the split will be, the larger the difference will be between the ground state and the excited state. That means it will absorb higher energy colors, like on the violet end of the spectrum. Whereas something like iodine or bromine, which has a very low electron density or charge density, is going to absorb lower energy colors like red or orange, since there's a very small difference between the ground and excited state in the d orbitals. Let's look at this specific example of copper with the coordination number of 6. The first example has all of the ligands as H2O, somewhere in the middle of this series. So that's going to absorb more of a red-orange. It's on the lower end of the spectrum. If some of those ligands are, instead of being all water, if some of them are ammonia instead, ammonia would then have a higher charge density, and it's going to cause it to absorb something a little higher on the spectrum, maybe a little light, yellow light being absorbed. So you're going to get a deepening of the color from pale blue to deep blue. As you're getting more and more splitting, that's a more energetic wavelength being absorbed. You may have been curious about the substance abbreviated EN that appeared in the list before. This is an abbreviation for a substance called a biodentate. Bi actually means two, of course, so this actually indicates that there's two attachments to the metal ion. So the two nitrogens shown in this example, both of those nitrogens would actually attach to a metal ion. This is going to affect the coordination number as well, because the coordination number is actually defined as the number of lone pairs attached. So it makes it a little harder to count the ligands, because we would actually count this ligand as 2 for the coordination number. So it gets a little bit complicated. For now, it should be in your list. You should be aware that there is an organic compound that is part of this activity series, but we're not really going to get into details of these complex ligands that attach in multiple ways. But it is what the EN stands for there, bidentate. Now let's move on to the third factor, the factors that describe this amount of splitting or distance between the d orbitals, and that would be the number of d electrons present. So basically we're referring to the oxidation number. That oxidation number is going to tell me how many electrons have been lost. For example, with the manganese ion, we could figure out if we've lost 2, 3, 4, how many electrons we've lost out of first, of course, the 4s orbital, and then starting to remove electrons from the 3d orbital. So here's a picture of some different oxidation states for the manganese ion, the ion that had the most possible oxidation states, and you can see a big range of colors, everything from purple to green to brown. We've got precipitates, translucent colors, almost clear colors, lots of different variety of colors depending on the number of d electrons, or the oxidation number of the central ion. And the very last factor that affects the splitting is the shape of the ion. So these are the 4 basic shapes that we went over in respect to the different types of coordination numbers. The coordination number of 2 would be linear. Coordination number of 4 could be either tetrahedral or square planar, depending on if there are other lone pairs attached. And then a coordination number of 6 would be octahedral. This is going to affect the splitting in the same exact way that the electron density would, depending on what the ligands are. So this is talking about the charge density around the central atom, just based on how spread out they are in the different shapes. So something that's more dense is going to cause more splitting. Keep in mind, just because a ligand causes splitting in the d orbital, that may or may not result in a color. If there is no allowable transition between the ground state and excited state portions of the d orbital, then there wouldn't be a color, because there would be no colors absorbed from the white light. It would still be all white light. And zinc is not the only substance that exists as colorless. Some other atoms also have specific cations which would also produce colorless solutions. So a couple examples here, we see the scandium +3 ion, which would lose the 4s electrons both, and then the first 3d electron, so it would be completely like our noble gas. And then copper also, the +1 charge, would lose the 4s electron. And remember, copper was one of the exceptions to Aufbau's rule, so it would steal for its 3d to have a completely full electron and only have the 1 valence electron to start with. So the +1 ion would just lose that 4s electron, leaving only 3d10. Completely full d orbitals, completely empty d orbitals, these will not have transitions, and therefore they would be colorless. And last, let me amend my little rant about how IB would not give you credit for the word clear if you meant colorless. Apparently AP agrees as well. So anytime you're trying to describe a lack of color, make sure you use the word colorless. The word clear is meant more along the lines of being translucent or see-through. The word colorless is the perfect description for what happens when you have completely full or completely empty d orbitals. And that completes Notes F. There is a demonstration that goes along with this about colored complexes, all about the iron ions. So make sure that you watch that demonstration, fill out that Edpuzzle online, and also submit a copy of your data table. And that'll actually tie up all of the Chapter 3 notes. So good luck, guys.